Hi, my name is Chris Clarke, and today I'm going to be talking to you about our paper on reactive video, adaptive video playback based on user motion for supporting physical activity. Videos are a really popular medium for learning physical movements and exercise due to the convenience they offer, with users able to access content on demand whenever they want, and often at a much reduced cost compared to gym memberships or personal trainers. Due to the proliferation of online video platforms, a lot of high-quality content is easily accessible. There is a wide variety of videos available from a diverse range of instructors because the barrier to entry is so low for content creators. This results in access to guidance and instruction from world-class experts. A personal trainer may adapt the intensity of a routine to an individual because they might be a beginner or due to physical limitations. Videos cannot respond in a similarly useful way and interaction is limited. Reaching for the remote or the device itself breaks flow and immersion, and whereas touchless technologies such as voice input offer a compelling hand-free alternative, in isolation they can only be used for the issuance of explicit commands. To address this, we introduce reactive video, a system which uses adaptive video playback for a more immersive experience and to better assist in learning new movements. Here's an example showing the system in action. Adaptive video playback infers the pace at which a user is performing a physical activity and dynamically adjusts the playtime so that the video reflects the user's movements. The system is designed to work with existing video content, providing a level of interactivity without additional burden for content creators. We also incorporate real-time guidance and feedback mechanisms to better support users and encourage safe and correct form. This is primarily achieved using motion trajectories to demonstrate upcoming movements, with overlaid graphics used to show how well the user matches the current movements. In this example, the video is adapting to the user based on only their hand movements, meaning that feedback can be provided independently of compound movements, in this case involving the legs. For the remainder of the talk, I'm going to focus on the adaptive video playback element and explain how we adapt the playback of the video based on the user's movement. For this, we took inspiration from direct manipulation video players, which I'm going to briefly introduce. In contrast to using a temporal slider, direct manipulation video navigation allows users to browse video clips by directly manipulating their content. Instead of dragging the slider, users can drag the objects along their motion trajectories to any desired position. The concept of direct manipulation video navigation underpins our implementation of adaptive video playback. We extract the skeleton of the instructor, for example using OpenPose. And the user's skeleton is captured in real time, in our case using a Microsoft Kinect. The principle is then to match the user's joints with the instructor's to adapt the playback. However, there are unique challenges that arise when we consider adaptive video playback in contrast to traditional direct manipulation video navigation. Traditionally, direct manipulation video navigation is used for seeking in a video, but adaptive video playback is used to continuously adapt the playback, which should be smooth for the user experience. The underlying concept of direct manipulation is not really applicable in a sense because ideally the video reacts seamlessly to the user. Temporal ambiguities occur when there is little or no movement of the object in the video, which can cause erratic jumps or are skipped altogether. Draglocks posed ways of solving this based on altering the trajectory of the object's handle. However, this is not applicable for the case of adaptive video playback, where the user should be able to intuitively navigate pauses without breaking the immersion. We also need to take into account different users who may use the system, and this includes differences in camera perspectives between the input and recording devices, and the physiological variability between the user and the instructor. We also have to consider that a user's internal intentions may not be accurately reflected in their movements, and a user's ability to follow a movement is dependent on their sensory motor synchronization. This is exacerbated by sensing inaccuracies. Previously, direct manipulation video navigation has been used with input modalities such as a mouse or a touchscreen, in which one point of input is used to control one object's trajectory. In contrast, we look at the case where there are multiple control points that can be used to calculate the appropriate playtime, as a single control point may not contain enough evidence. We implemented adaptive video playback in 3 stages. The first spatially aligns the user's skeleton to the instructor's in order to compensate for differences in physiological variability and/or different camera perspectives between the input and recording devices. Please see the paper for more details on this stage. The second stage is to estimate the playtime in the video which corresponds to the user's movement, and I'm going to discuss this in more depth. And finally, we have the rendering stage, which is where we determine what to show to the user. This can incorporate additional filtering steps to ensure a smooth output, and also, depending on the context, we may want to vary what we show to the user. For example, if a user is learning a movement, we can add an offset so that they are always following the video. Okay, let's take a deeper look at playtime estimation. Previous approaches for direct manipulation video navigation use a single best guess of which playtime to show. Here are 4 different approaches from different authors that have been used in the past. The first thing they do is minimize the spatial distance between user position and the object in the video. And this is to minimize the spatial indirection. So here, one would select the playtime closest to the user's cursor position. However, it is also important to minimize the temporal distance. We don't want discontinuous jumps in the playtime, which can arise from intersecting trajectories or recurring movements. Now, the problem with these previous approaches is that they all rely on a single best guess of the playtime and do not take into account uncertainties in the system from the sensors and the user. Beyond the most simple cases, we found these simply did not work well in the context of reactive video. Probabilistic approaches represent information as probability distributions over a range of guesses, whilst taking all evidence into account, and are typically more robust in the face of uncertainties. The discrete Bayes filter represents probability as a histogram, and the state we are trying to estimate is the playtime. For each discrete frame in the video, we have an associated probability which corresponds to our belief of where the user is in the video. A discrete Bayes filter uses Bayes' theorem to update the histogram based on 2 key stages. The prediction stage uses a very simple process model to represent how we anticipate the user will behave. We assume at each time step that they will proceed with unit play speed. However, we are not certain of this because they could be going slower, faster, or in reverse. So we convolve our belief with a Gaussian kernel, which represents the uncertainty in our process model. The second stage updates our estimation by incorporating measurements of the user's pose. We calculate the Euclidean distance between each control point from the user to the instructor after they've been spatially aligned. And we take into consideration user and sensor errors using a Gaussian likelihood. This is a drastic simplification of the underlying measurement probability, which could be dependent on a number of factors, including user skill, movement difficulty, or the number of joints measured. The final estimation is then either the frame with the largest probability, or we can take an average over all the frames. We also investigated the use of a particle filter. Instead of a histogram, this uses particles, where each particle represents a continuous value for the playtime, which is not confined to discrete frames. Rather than assuming unit play speed, the particles themselves estimate the play speed, which has ramifications for how temporal ambiguities are navigated. Without any useful evidence from the user's poses, the Bayes filter will default to unit play speed, whereas with the particle filter, it is more likely to continue with the play speed at which it was running prior to encountering the temporal ambiguity. To demonstrate the feasibility of adaptive video playback and evaluate the probabilistic approaches, we conducted an evaluation. We used 6 different exercises specifically chosen to be simple enough for inexperienced users to complete, whilst also containing challenging elements for the approaches, such as temporal ambiguities, arc length, and directional discontinuities. We recruited 8 participants, and for each video, users had to mimic the on-screen exercise, but we wanted to elicit controlled tempo changes from the participants. We therefore use 4 different modifications for each video, which include pauses, changes in tempo, and parts in which the user performs the exercise in reverse. This results in a dataset where we can post-process the videos and try different algorithm parameters. When we plot the playtime estimates of the algorithm against the original video, we would expect it to track according to the tempo modification used. So here is an example where the red line represents the playtime of the video that was shown to the user, and the blue is the output of the algorithm using adaptive video playback. In general, when you take into account user error, the approaches were able to successfully adapt their playback across the different videos, and overall, the discrete Bayes filter outperformed the particle filter. Exercise C was particularly problematic due to the high level of directional ambiguity, and this is because it is ill-defined as to which direction the algorithm should play when users reverse playback at the turning points. We found the reverse variants to be the most problematic to accurately track. However, we wouldn't really expect these to be used very often or for prolonged periods. Throughout the development of Reactive Video, we had several visitors to the research lab to test out the system, and we gained some very interesting insights which require further investigation. As reported in previous research, we noted how the feedback provided to users can be problematic for learning the underlying movements. We coined this the dot game, where users focus on aligning the dots provided as feedback as opposed to focusing on the underlying movements. We observed that most users of the system, including the participants of the data collection, naturally mirror the instructor's movements. However, some users preferred non-mirrored interaction. This is curious from an embodiment perspective. To what extent do users see the instructor as a reflection? And how much does the synchrony between user and instructor increase immersion and feelings of engagement? We also encountered a really interesting causality dilemma. Traditionally, a video does not adapt continuously to a user. A user passively watches or copies the video. In reactive video, as the name suggests, the video is reacting to the user's movement, and therefore the user is the causal source. The user leads and the video follows. However, when users are learning a new skill or movement, they will attempt to mimic the instructor. With adaptive video playback, this can lead to a causality dilemma, a subtle circular feedback case where it is not clear who is leading. Is it the user or is it the video? Okay, to wrap this up, we've introduced reactive video, which enhances the utility of existing videos and is designed to increase immersion by providing seamless control of the video playback without breaking flow. By taking inspiration from direct manipulation video navigation, we can adapt the video playback to the user's movement, and the unique challenges that accompany this can be alleviated by taking a probabilistic approach to the problem. This is a really exciting space to be working in, and we have only scratched the surface. If you'd like to know more, to get involved, or if you have any other questions, then please email me. Thanks for listening.